Before that, I must say my today's class will be on the discussion of transportation problem. And if you can recall that this particular type problem has already been discussed with you in the very beginning in one of my earlier classes. And I told you the transportation problem is one kind of linear programming problem. And I showed you how to write its mathematical model and how, but I didn't tell you how to solve this kind of problem. After that, I introduced the graphical method of solving a linear programming problem. But then I also told you that graphical method has its own limitation, and it is only applicable in its true sense if the number of variable is exactly equal to 2. If the number of variable is equal to 1, then there is no meaning for solving it because it is pretty obvious. But if the number of variable is 2, then you can apply graph. But if the number of variable is more than 2, then if you can deal with the three-dimensional figures, then you can possibly tell me that, yeah, graphical method is can be generalized to 3D. 2D figures can be generalized to 3D, and 2D regions can be generalized to 3D regions. But I don't think that would be a very good solution. So to deal with more than two variable cases has its own methodologies, which hasn't been discussed yet. And also, I am a little bit of hopeful of the fact that probably very soon, if everything goes well in West Bengal, then physical classes will be starting. So I am keeping that discussion of how to solve linear programming problem using some other kind of method for the linear programming with 3 variables. I am keeping this for the time being for physical classes. Today, before I started this class, I was thinking, what would I teach you today? And I ultimately hooked on to this transportation case because I thought I would be able to deal with this transportation problem in this virtual whiteboard. But although I have to use my finger to write something, but yes, probably I can deal with that. But the methodology of solving a linear programming problem with 3 variables is a kind of algebraic method which is very hectic and tedious. So I am a bit afraid that I would not be able to use my fingers and the virtual whiteboard to show it to you properly. But if the situation doesn't permit me to go for the physical classes, then later we have to stick to this particular online portal. So I'm keeping it for some later purpose. So today I'm going to discuss what is transportation problem and how to solve it. What is transportation problem has already been told to you, but since I'm today giving you the solution procedure, so I'll start from the scratch. I will ask all of you to write this question quickly in your copy. You can write the entire question quickly, or you can write the highlighted portions only. So just to give you some time so that you can write it properly, I am reading it out for you, this particular problem. And that during this time, you will be able to copy it completely in your copies. So the problem is given in this way, that let there be 3 factories, 1, 2, and 3, in which a certain product is manufactured. Why did I highlight this word, a certain product is manufactured? Because it is one of the fundamental conditions imposed on the transportation problem, which says that you can consider any number of factories, okay, and from one factory to another destination, you are going to send the products which is being manufactured in your factory. But suppose you have 3 factories and 3 destinations. You cannot say that your factory 1 is producing refrigerator and factory 2 is producing TV and factory 3 is producing radio. here in this phase of transportation problem, we shall consider this. We shall consider that all these three factories which you have, they are producing only one type of item. Either it is radio or refrigerator or TV, whatever, but only one type of one item. Every every factory in this transportation chain is producing a single type of entity. So therefore it is highlighted a certain product is manufactured. And let there be 4 warehouses, Roman 1, 2, 3, 4, situated at various places in which the manufactured items from each factory are sent to these 4 destinations. The transportation cost of sending unit quantity, again this is highlighted. Transportation cost of sending unit quantity of the product from factory 1 to warehouse 1 is rupees 19. So when we shall consider the transportation matrix, and in the matrix, in the cell, we shall put the costs. Remember, this cost is the unit cost. So suppose the factory 1 is there and destination 1 is there, and I'm in the cell 1 1, I'm putting rupees 19. That means you have to shell out rupees 19 in some units, maybe in 1000 units or maybe in 100 units. Rupees 1000, rupees 19 for transporting one item from the factory 1 to destination 1. So therefore it is called unit transportation cost, or transportation cost of sending unit quantity. Unit quantity means one particular quantity. Similarly, the unit transportation costs of the product from 1 to Roman 2, Roman 3, Roman 4 are rupees 30, rupees 50, rupees 10. So you see the coloring of these two are matching. Roman 1 to numeric 1 to Roman 2, 3, 4 is having unit transportation cost as rupees 30, 50, 10 respectively. Then I have matched these two colors, okay, because they are related. When I send this particular item, unit quantity of that particular item from factory 2 to these 4 destinations, 1, 2, 3, 4, I have to shell out money, respectively rupees 70, 30, 40, and 60. And this last item is gray colored when I am matching the factory 3 to these 4 destinations. So 3 to 1, 2, 3, 4, this particular thing requires unit transportation cost as rupees 40, rupees 8, rupees 70, and rupees 20. The space capacity of the warehouse 1, 2, 3, and 4 are 5, 8, 7, and 14. Space capacity means if you are sending TVs or say any item, refrigerator or radio, whatever you are considering, Roman 1, this particular warehouse can contain 5 of these items in it, not more than that. So this is its limitation. So therefore it is called space capacity. Roman 4 can contain 14 of these items in it. And on each day at the factories, there are some other kind of limitations. These are called factory capacities or manufacturing capacity. That Roman 1, this numeric 1 factory can produce 7 of these items per day. Numeric 2 factory can produce 9 of these items per day, and numeric 3 factory can produce 18 of these items per day. So our first job is to formulate this particular given problem. So let us first discuss the formulation portion. Okay. So since I'm starting from scratch, I'm showing you this formulation portion once again. Achha, by the by, all of you write your roll numbers in the chat box. Probably, I hope that you have successfully copied this particular problem. And if you have done so, you write your roll numbers in the chat box.
We don't have our roll numbers.
Okay, you write your names in the chat box so that I can save it. I have your names. So you write your names in the chat box. Okay, sir. Or you can use your serial numbers. So it would be much better if you write your names in the chat box. Okay, and I hope that you have completed writing this particular question. So don't have to forget about this B and C portion. B and C portion, I'll again show you, because let me proceed stepwise, one after another. So first of all, corresponding to the given problem, I shall discuss the formulation part. The formulation part has already been discussed with you, but since I'm starting from scratch, I will first show you the formulation, then I will go to the solution process. I'm scrolling down. See, this is the transportation table. So you can quickly copy this particular transportation table. I am also copying it in my copy, because I have to use it in the whiteboard. Okay, so at a time I can share one item only. I cannot share the whiteboard as well as the PDF file together. So I'm also copying it in my copy. You also do it. So you copy this particular matrix, and then I am telling you how this matrix is obtained. The matrix is obtained in a very simple way by following the conditions given in the question. Okay, and you see, factories are named as Roman 1, 2, 3, 4. Sorry, the warehouses are named as Roman 1, 2, 3, 4. Factories are named as 1, 2, 3. The warehouse capacities are written here, and the factory capacities are written here. Warehouse capacities have been termed as capacity. Factory capacities have been termed as availability. And now if you have copied the question, probably you have seen, probably you can see that this Roman 1 factory is sending unit quantity of the item produced in it against rupees 19 to Roman 1. The factory 1 is sending unit quantity of the item produced in it against money rupees 10 to the factory Roman 4. Roman 3 is, the numeric 3 is sending unit quantity of item produced in it to the factory, to the warehouse Roman 2 against the money rupees 8. And in this way, according to the costs given in the problem, all these cells have been filled up with the corresponding values. Okay. Similarly, the destination capacities or warehouse capacities have been written over here. Roman 1 has capacity 5, so 5 has been put over here. Roman 2 has capacity 8, so 8 has been put over here. Roman 3 has capacity 7, so 7 has been put here. Roman 4 has capacity 14, so 14 has been put over there. So these are all the factory capacities, or you can say, sorry, the warehouse capacities, or you can say these are factory capacities. Destination capacities or space capacities. And if we consider the rows, 1, 2, 3, there are 3 rows. So Roman 1, the numeric 1 corresponds to 7. That means per day, the factory 1 can produce 7 items only, not more than that. Per day, numeric 2 can produce 9 items only, not more than that. And per day, the numeric 3 can produce 18 items only, not more than that. These things are all given in the question. This portion is the highlighted portion. This is extra, which I have calculated. What is it? It is the sum total of these quantities. If you add 7, 9, and 18, you will get 34. And also, if you add these quantities 5, 8, 7, and 14, this is called this number 34 will again come. So thus you can say the column total here is 34, is same as the row total here, which is also 34. And this is quite expected in transportation problem. In every transportation problem, this equality is expected. And if there is equality, if the column total, if the sum total of the factory capacities is same as the sum total of the destination capacities, such a transportation problem is called balanced transportation problem. And the process which I'm going to show you today, all these processes have been derived to solve a balanced transportation problem. But if you ask me what happens to the transportation problem where the factory capacity, the total of the factory capacity and total of the destination capacities are not same, such a transportation problem is called unbalanced transportation problem, but the unbalanced transportation problem can also be dealt with. So first of all, we shall study how to solve a balanced transportation problem, and then we shall generalize the things in due course. What will be the mathematical model of this transportation problem? By mathematical model, we mean that we want to solve this transportation problem with respect to some variables. So first of all, you have to identify what sort of variables you must consider over here. So you see what I'm writing over here. I'm using 4 different variables which have been named as small x subscript 1, 1, x12, x13, x14. What are these subscripts represent? What are these variables represent? These variables represent, say x11, this represent, we are to send x11 items from factory 1 to destination 1. x14 represent, we are to send x14 items, x14 number of items from factory 1 to destination 4. And these values.
Sir, your voice is breaking, so we cannot
okay,
understand.
it's just because of the network issue is there. Can you hear me now?
No.
Can you hear me now?
Sir, your voice is breaking.
Sir, your voice is breaking a lot.
Sir, you are not audible at all.
What about now?
Yes, sir. Yes, sir.
Now it's
okay. Okay.
Okay.
Yes,
okay,
sir.
sir.
Yes, sir. Yes, sir.
Okay, so what I was saying that we want to find the mathematical model with respect to what? With respect to some variables. What are these variables? Since unit transportation costs are given, I don't know how many items must we send from factory 1 to destination 1. So I'm saying that let x11 be the item which has to be sent from factory 1 to the destination 1. Similarly, x12 be the items which is to be sent from factory 1 to destination 2. x13 be the items which is to be sent from factory 1 to destination 3. And similarly x14. But all these values, all these variables are unknown. Their values are not known to me. And since you see, since the unit transportation cost, I am going to apply a unitary method over here. Since unit transportation cost for this particular cell is 19, and I am supposed to send x11 item, so the transportation cost for this, total transportation cost for this particular cell will be 19 into x11. Similarly, total transportation cost for this cell will be 30 into x12. Total transportation cost for this cell will be 50 into x13. Total transportation cost for this cell will be 10 into x14. And that is for row 1. Considering this, considering a similar technique for all these rows, and by naming the variables properly, I have mentioned here x11, x12, x13, x14. Then for row 2, you can mention x21, x22, x23, x24. For row 3, you can mention x31, x32, x33, x34. You can get the total transportation cost for all these rows. So in general, the total transportation cost for entire matrix will be denoted by 19 into the variable plus 30 into the variable you have considered plus 50 into the variable you have considered plus 10 into the variable you have considered plus 70 into the variable you have considered. In this way, we shall reach up to 20. So I have shown here the total transportation cost as 19x11, 30x12 plus ... plus 20x34. So there will be in total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 variables, and 12 of these items have been added over here, which is the total transportation cost. And we always try to minimize the transportation cost. So this transportation cost is a minimization type of problem. So since the transportation cost has been denoted by Z and the total transportation cost is this, so the basic problem of the transportation problem is becoming as minimize the transportation cost Z, which is given as follows, and that becomes our objective function. Objective function is the objective of the experimenter, so that he can deal with the variables in such a manner so that he can minimize or maximize the variable present in the objective function as per the situation. If it is a maximization type of situation, he will try to maximize it. If it is a minimization type of situation, he will try to minimize it. Transportation cost involves transportation cost, and therefore this cost always has to be minimized. Profit is to be maximized, cost is to be minimized, loss is to be minimized, and so on. So since transportation problem involves transportation cost, we are to minimize it. So it becomes a minimization type of problem. Okay. Then there comes some constraints. Now you already know that factory capacities are given, and the total number of items present in factory 1, or you are supposed to send from factory 1 to factory to destination 1 is denoted by X11, and similarly we have considered X12, X13, and X14. All these items, if you add them together, then these items, the sum total of these items will be or should be less than or equal to the total factory capacity, which is 7. This sum total of this cannot increase the factory capacity. It is always lesser than this. So thus you have got one particular constraint which is given over here. Similarly, for the second two rows, the second row and the third row, you have the constraints as the total of these items which are to be sent, which are assumed to be sent from factories to the factory 2 to the destinations, should be less than or equal to 9, which is the factory capacity of 2. And similarly, the total of these items, which are the values, the number of items which is to be sent from factory 3 to the different destinations, the sum total of these items must be less than or equal to 18, which is the factory capacity of 3. So all these things, all these constraints is actually becoming the availability constraints. These are called availability constraints. And please mute yourself. Okay. And the warehouse this particular transportation problem has another kind of constraint, which is coming from the space part, space capacity portion. So I was here in this particular set of constraints, I was adding the variables row wise. You see, I have considered the first row, I added the variables row wise. For the second row, that has been added row wise. For the third row, added row wise. But instead of doing that, if I add them column wise, so we shall have, since there are 4 columns, we'll have 4 constraints. So X11 plus X21 plus X31 must be greater than or equal to 5. And 5 was not the factory capacity, 5 was the, this number 5 is the space capacity. So in this particular case, we are to set the things in such a way so that what we want to do when we send something into the warehouse or godowns. Godown has certain kind of capacity, but we want to put things greater than this, and the godown space becomes stuck with the things. We try to put the things over there, which actually gets increased from the it becomes larger than the space capacity of the things. This is the human nature. You are traveling somewhere, you are filling your suitcases with some items, and this particular suitcase of yours has certain capacity. which which means that it can contain this many items in it properly. But if I go by the theoretical approach, then to carry all the items which is required for the travel purpose, I have to, for one person has to carry more than one suitcases, so 2 to 3 suitcases. So it is not possible. So what we do, we try to get the things and we try to force it in some way so that it gets some kind of place here and there inside your only one single suitcase. So the number of items we are actually sending to the suitcase is greater than the suitcase capacity. So therefore the greater than symbol has come over here. Don't think that since the space capacity is 5, it should be lesser than this. So greater than symbol has come over here because of this reason. Okay, so all these items, if you add them column wise, becoming greater than 5.
Sir, can you repeat, sir?
Which
Can
part?
you repeat
Which part?
Why it is greater than?
Greater than. Suppose.
Why you have mentioned?
Yeah. I'm repeating it. If you are traveling somewhere, you carry this bag, you want to carry a particular bag with you. Suppose you are traveling by air, and you have bought a ticket for Indigo. Indigo is giving you the permit of carrying 25 kg in the cabin luggage. So you cannot exceed it. 25 kg cannot be exceeded. So what you try to do, your bag has some kind of capacity. You want to put more items in it, so that you always think that I want to carry only one single bag with me. So if you want to go by the theoretical approach, that means if you think that I shouldn't take the number of items should always be equal to the or lesser than the capacity of my bag, then you cannot take all the items together in a particular bag if you go by this particular approach. So if you want to go by this approach, then you have to carry more than one luggage. For a single person will always carry more than one luggage. So it is not a viable solution. Nobody does like this. So we always try to do things in particular way so that we know the capacity. The bag has a certain capacity. It can hold the items properly in it, but we try to put things into it in such a manner so that everybody adjusts with itself, and the things, much more things get some kind of space in the limited in your bag, which has limited capacity. So I am putting things more than the capacity of the holders. So this is the scenario which happens for the destination warehouses also. Warehouse has some kind of capacity, but we always try to send many number of more items than the space capacity, and we shall try that the warehouse will somehow contain all these items sent to it in a proper way. So therefore the greater than symbols have come over here, not lesser than symbols. But if you look into this carefully, you will see that in whether it is less than or equal to symbol or greater than or equal to symbol, less than symbol or greater than symbol, equality is always there. I have considered equality here also in this particular set of constraints. I have considered equality in this particular set of constraints. So lesser than and greater than, these two things will fight with each other in such a way so that everything is properly adjusted. So this set of constraint is called an requirement constraints. And this set of constraint is called availability constraints. And all these variables, x11, x12, and this 12 variables, these variables are always non-negative, because it gives you number of items to be sent from factory to the destination. You cannot say, I will send minus 10 items from this particular place to that particular. So all these are non-negatives. You can say that I will send no item from factory 1 to destination 4. So it can be 0. The lowest value is 0, but cannot be negative. So this constraint is there, and you know this is called the non-negativity constraint. And another type of constraint, as I have written over here, which creep in over here, that sum of the space capacity is should be always equal to the sum of the manufacturing capacity, which is 34 in this particular problem. Such a problem, if the total of the space capacity is same as the total of the manufacturing capacity, such a transportation problem is called the balanced transportation problem. If they are unequal, that means one is more than another. If there may be two cases. Either the space capacity is more than the factory capacity, or factory capacity is more than the space capacity. In both the cases, the transportation problem is called the unbalanced transportation problem. But here I'm dealing with a balanced transportation problem. So this is so we have got our objective function, we have got our constraints, we have got our non-negativity restriction, we have got our balanced condition. So in this way, we have actually modeled the transportation problem. And once we find the model, the remaining portion is to deal with the transportation problem and to find its solution in a particular way so that the objective function gets minimized. So my time is almost over for the first session of today's class. Let this session be cancelled, and then I'm again joining in to discuss how to solve this particular transportation problem. Okay, so there are different methodologies. I will tell one by one, one after another. After joining in, you don't have to write your names once again in the chat box. It has been saved already. Okay, just wait.